Hello, my name is Gefersom. I am a master's student in the graduate program in Applied Computing at Unicinos, Brazil. In this video, I will present the work entitled Binary Segmentation of Seismic Facies using Encoder-Decoder neural networks. This work fits into oil exploration, which plays a role in modern economy, providing products such as plastic, gasoline, cosmetics, and food. In the initial phase of exploration, it's necessary to investigate sedimentary layer characteristics that indicate the possibility of oil storage. To this end, we can drill wells or use reflection seismic. Reflection seismic is a method of geophysical exploration capable of providing the structures of sedimentary layers of a region. In this method, generated elastic waves ascend to the interior of a region. Emitters on the surface can artificially generate these waves at sea or on land. When the waves pass through different layers of sediments, part of their reflected energies are captured by sensors on the surface. All seismic data will be processed to create a visual representation of the sedimentary layers. With seismic reflection, it's possible to have the first contact with the layer organizations in an area without drilling a well that can cost a large amount of money. After generating seismic data images, the interpretation phase begins. In this phase, interpreters use techniques to enhance geological properties or manually mark the positions where they would appear. This work takes a lot of time and needs specialized professionals to perform the tasks of interpreting and analyzing the results. This image represents some seismic sections, which can be understood as geometric planes. This image is from a 4 gigabytes seismic volume that contains 1,000 sections that the interpreter may need to analyze. From what we have seen so far, we can highlight three important challenges in this process. The amount of seismic data to be analyzed may have gigabytes or even terabytes. There may be a need to perform many tests with various techniques for enhancing geological events. Specialized and experienced professionals are required. Thus, in this work, we seek to reduce the time that interpreters spend on their work. We also aim at making seismic interpretation reproducible and to create a tool capable of delineating seismic faces geometries. In the literature, we noticed that much of the works focused on segmenting one type of seismic phase geometry. The neural networks tend to have a large number of parameters, and inappropriate loss functions for segmentation have been used. To perform this segmentation task, we propose a deep neural network for face segmentation, or simply DNFS, which is based on UNet and SDNet. We optimized the number of network parameters with the help of a composite loss function from the linear combination of cross-entropy and Jacquard loss. Cross-entropy is responsible for classifying pixels as transition between areas, and Jacquard is used to measure the intersection between predictions and the expected output masks. To perform binary segmentation, we created a dataset in which the change in inflection patterns called seismic phases was represented by a black line. Here, we show an example of seismic image. This other image shows a possible interpretation of the seismic using different colors. The third image represents the binary mode, and the last image shows a combination of binary mode and seismic image. We highlight that there are no standard datasets for binary segmentation or seismic phases. Since the number of images for training was small, we created new images using the data augmentation technique. We extracted small segments from the grayscale image to be used as the input to the neural network and extracted the corresponding segment for the binary images to be used as the output to the neural network. We further augmented this number of images using horizontal flipping and rotation. Due to the significant variation in seismic phases, geometry in different exploration areas, apply a single trained neural network model becomes problematic. So, we created a small neural network from some experiments, which is capable of being trained in a short time. The NFS consists of two main parts. The first encodes the input image, and the second reconstructs an output image aimed at minimizing the difference to the labeled segmentation mask. The NFS has a smaller number of filters in the inner layer blocks and in the connection between these parts. We use skip connections to enable the propagation of the gradient error between layers. In blue, we have the convolutional layers, and in purple, the transposed convolutional layers. Here, we show the scheme used to vary the number of network parameters. There are 18 neural networks variations. The omega value was changed to each of the factors shown in the table. The red rectangles contain the DNFS and STNet and UNet baseline networks. The different factors change the neural network sizes, which made DNFS have a much smaller number of parameters and disk requirements than the other networks. For the training parameters, we used a dropout at a rate of 10%, a batch size varying according to the numbers of parameters, a learning rate of 0.001, and a maximum of 500 epochs. Another distinguishing contribution of this work is the use of a composite loss function that better encompasses the needs of seismic phase binary segmentation. Our loss function combines Jacquard loss and cross entropy. The weight we give to Jacquard is defined by means of parameter beta. We performed 5 experiments to determine the best value for beta. Here are the equations of the composite loss function and the experimental values for the beta. The chosen value was 0.5, and this value led to high accuracy levels. The image with a red rectangle represents the best linear combination of cross entropy and Jacquard loss that we found. As for the evaluation metrics, we used accuracy, intersection over union, and the percentage of black pixels correctly classified. The next slides show experimental results and the comparison of predicted images by DNFS, STNet, and UNet networks. This table shows factors, training time, black pixels percentage, the total number of parameters, and disk size in our experiments. STNet with a factor of 32 and UNet with a factor of 64 are the baselines for our comparison. Note that the accuracy of STNet rose slowly and presented the worst accuracy among all runs. DNFS and UNet have similar accuracies. DNFS with a factor of 8 was the one with the best accuracy, even though it's not that much bigger than the others. However, DNFS maintained its accuracy even when the parameters increased. The same was not true when observed for UNet. With a factor of 64, it lost much accuracy. Finally, we present a comparison between the predictions of the networks. As can be observed, noise levels increase steadily as the net accuracy increases. This problem was not observed in the predictions made by our network and by UNet. The main limitations of our work are the variation in pixel intensity made the accuracy vary. We use a small amount of data for training. We also had a lack of datasets to validate the performance of the model. If you want further information about our research, please check out our paper. Thanks for watching.